Hello everyone, we're going to talk about section 5.3, which is going to be about annuities, future values, and sinking funds. So we've already heard the term future values, but in this section we'll be figuring out how to calculate annuities and then also how to calculate sinking funds. So we've only really been analyzing lump sum deposits and payments, but many financial situations involve a sequence of payments at regular intervals. So for reasons that become more clear later on, we want essentially this definition here, which we say, if x is a real number and n is a positive integer, then 1 plus x squared plus x cubed plus, and we go all the way up to x to the power of n minus 1 is equal to x to the n power minus 1 divided by x minus 1. So this is just kind of a basis equation that we have for saying that we want sequences of payments as opposed to just lump sum payments. So we'll see that the equations that we see later on are going to look a little bit more like equations like this to represent that sequence of payments that we're going to have, because we know that not in all financial situations it's going to be drop one lump sum and then we make investments or anything like that. We know that there's a lot of situations that involve payments during every period or things like that, or maybe investments at different periods. And so that that reasoning that we have needs to be expressed in different equations. All right, so starting just with ordinary annuities, we see a sequence of equal payments made at equal periods of time is called annuity. So this means that if we have an entire sequence of payments that we have in their equal periods and their equal payments, we call that annuity. Then we have the time between payments is the payment period, so it's pretty self-explanatory. The time from the beginning of the first payment period to the end of the last payment period is called the term of annuity. So we have that annuity, the term of it is going to be from the first payment period to the very last payment period. So that entire term that we're paying annuity. Annuities can also be used to accumulate funds or pay out funds. So this just means that it can be used to just continuously keep adding up funds, or we can use annuities to pay out maybe debts or things like that. So in this section, we're going to consider accumulating funds, and then in the next section, we're going to consider annuities that will pay out funds. So in this case, we're only going to be doing with the accumulation of funds using annuities. So the future value of such an annuity is the financial sum of deposits. So however much you've deposited maybe into a bank account or something along those lines, that's going to be your future value. Then we have, or it's considered the total amount of all deposits and all interest earned by them. So not just what we deposit in, but also the interest that we're going to use on it. Then we'll begin with our ordinary annuities where payments are made at the end of each period, and the frequency of payments is the same as the frequency of compounding interest. So we're going to see the same compounding periods here. So we're going to see, annually, semi-annually, monthly, quarterly, daily, things along those lines. All right. This section, similar to the last section, is a little content heavy as well. So there is going to be good chunks of content in here. So we want to start with the future value of an ordinary annuity. So the future value S of an ordinary annuity used to accumulate funds is given by S is equal to R times 1 plus I to the n power minus 1 divided by I. Or we can rewrite it in this different form, but we are not going to bother with that. We're only going to bother with this very first equation that we see right here. So this is what we're going to pay attention to. Well, we have that R is the payment at the end of each period, I is the interest rate per period, and N is the number of periods. All right, so we have this equation here, and like we said before, we're going to set up our equations similarly to this new kind of form where we're going to think about sequences. So we have here that we have, especially in the numerator, we see that we have this value to the n power minus 1, and that's going to represent our sequence of equations. All right, so let's put some of this into practice And we see example 1 here, which is numbers 3 and 7 in your book. We want to find the future value of the ordinary annuities with the given payment and interest rates. So for A here, we're going to have R is equal to $12,000 with a 6.2% interest compounded annually for 8 years. So we're just going to plug in all of these values into our equation, and then we will see what we get. So we know what R is. So we know that R is equal to 12,000. I is going to be 0.062. Since it's compounded annually, we don't have to divide by anything other than 1, that is. And we're compounding annually for 8 years, so we have N. It'll be 8 times annually is 1, so we know that N is equal to 8. All right, so we want to use this equation that we have up here, which we know this is going to be S is equal to R times 1, nope, that's I, 1 plus I to the n power minus 1 divided by I. So we're going to plug all of our values in. So we have S is equal to 12,000 times 1 plus 0.062 to the 8th power minus 1 divided by I. So we can simplify what we have inside of our parentheses first here. So we can end up getting S is equal to 12,000 times 1.062 to the 8th power minus 1 divided by 0.062. I did not write that the first time. So I invite you to pause the video and calculate this value on your own. And if you do, you should have gotten $119,625.61. All right. So we see here our future value with our annuities is going to increase by a lot at 6.2% for 8 years. Now we can move on to our next term here. So there we go. We know that R is going to be 1,200, or we have R is $1,200 at 8% interest compounded quarterly for 10 years. So we have R is equal to 1,200. I is equal to, we know at 8%, this would be 0.08 in decimal form. And we have that as being compounded quarterly, so we need to remember to divide by 4. Then we have compounded quarterly for 10 years, so this means that we have N with quarterly times years, so we have times per period times the number of years. So we get that N is going to be equal to 40. All right, and now since we know the equation that we need to put everything in, we can just go ahead and put everything into our equation. So we have S as well. We have S is equal to 1,200 times 1 plus 0.08 divided by 4 to the 40 power minus 1 divided by 0.08 divided by 4. All right, and since there's a lot of terms in this case, I invite you to calculate this one on your own. And if you did, you should have gotten $72,482.38. So we're seeing that when we work with future values of the ordinary annuities, we're seeing that our our final or future values will be significantly larger than the values that we start with. All right, now for example 2, which is going to be number 9 in your book, we want to find the final amount rounded to the nearest dollar in the retirement account in which the rate of return on the account and the regular contribution change over time. So this just means that we're going to start with a certain value and maybe interest, and then it's going to change at some point to maybe a different value with a different interest rate. So we see we have $400 per month invested at 4%, compounded monthly for 10 years, and then we're going to have $600 per month invested at 6%, compounded monthly for 10 years. So we're going to see the amount we invest and the interest rate change after 10 years. So let's start with our first period of time here. So we're going to name this 400 per month invested at 4% compounded monthly for 10 years. We're going to label this, we're going to label this 1, and then our $600 per month will be labeled 2. So let's just work on 1 for now. So if we have 1 here, we know that R is going to be equal to $400. I is going to be 0.04, and we're compounding monthly, so we know we have to divide by 12 for our number of periods. And then we calculate our N, so it's going to be for 10 years. So 12 periods for 10 years. So we'll have to do 12 times 10, and that's just going to equal 120. So we need to calculate this very first value. And since we know our equation, we get S is equal to 400 times 1 plus I, which is 0.04, divided by 12 to the power of 120 minus 1 divided by 0.04, which is being divided by 12. All right, so once again, I invite you to calculate this value on your own. And once you've done that, you should get 58,899.99 cents. So we can say that is about $59,000. Or, sorry, $58,900. I got a little too ahead of myself there. All right, so now we have that value. Then we want to calculate our second. So let's scooch this down here. And let's put our second one right over here. So now I want to do the exact same thing. So now we have a different number for R, and we also have a different value for I. So we know that R in this case is going to be 600. I is going to be 6% or 0.06, also divided by 12. And our period is going to be the same because we're still compounding monthly for 10 years. So we know that N will still be equal to 120. Now we can just calculate our value. We get S is equal to 600 times 1 plus 0.06 divided by 12 to the power of 120 minus 1 divided by 0.06 divided by 12. So once again, I invite you to calculate this value on your own. And you should get $98,327.61. But we want to round to the nearest dollar, so we know this is going to be about $98,328. All right, so we've calculated this first chunk of time versus our second chunk of time. And so we know that our first chunk of time, that is going to be the amount that we're going to make our investments on. So we can say here, our original $58,900 is earning interest at a rate of 6%. So we need to use our compound interest rate formula, our compound interest formula, which we learned in our last section, in order to get so this basically just means that since our first chunk of time we ended with this certain value, we know that for the next 10 years it's still going to be compounding monthly, but now we're compounding at 6%. So we need to use our compound interest formula in this case to get our first chunk of money essentially up to speed with the end value of our next 10 years, since we're still making that 6% interest on it. So we'll use this value, and remember our compound interest formula is just A is equal to P times 1 plus I to the n power. So we're going to say A is our future value, or $58,900. Or sorry, that is our present value. So we get, nope, get out of here. A is equal to 58,900 times 1 plus our interest rate, which is still being compounded monthly, so we still have to divide by 12. So 0.06 divided by 12. And our n is still going to be 120, still being compounded monthly for 10 years. So we still get 120. Once again, I invite you to calculate this value on your own. And you should end up getting $1,162.40, which, since we're rounding to the nearest dollar, we're just going to say that this is $107,162. All right, so we've essentially caught up our very first period of time with now our second period of time with the amount of interest it should have been earning. So we know that now after 20 years, so after both periods of time here, after 20 years, we have $107,162 as well as $98,328. And our question wants us to find the final amount in the retirement account. So our final amount will be both of these values. So the compound amount that we found from our first period in addition to the amount that we found from our second period. So our final amount is going to be 107,162 plus 98,328, and this is going to be $205,490. So we know that this is going to be the final amount in their retirement account after investing these amounts of money at different interest rates for separate periods of time. And by these periods of time, I mean out of 20 years, it got cut in half to 10 years and 10 years. All right, so that was a little bit more complicated. So now I want to move on to this idea we have of sinking funds. So a sinking fund is a fund set up solely to receive periodic payments. If payments are equal and they're made at the end of regular periods, they form an ordinary annuity. So a sinking fund is just a fund that is purely set up so that it will receive periodic payments. So all it really does is just accumulate deposits that we get, which this whole section that we're talking about is about accumulating funds. So a sinking fund is just there to accumulate funds after periodic payments. So for our first example here, which is also checkpoint 5, or our example 3, so our first example on sinking funds. It's also checkpoint 5 in your book. And we have Pete's Pizza deposits $5,800 at the end of each quarter for 4 years. So we can already see that this is a sinking fund. We're depositing money at the end of each quarter for 4 years. So this fund, whatever we're depositing this money into, is a sinking fund because it's receiving these payments periodically, which are also made at the end of our regular periods. So this is also an ordinary annuity. All right, so for part A, all we want to do is find the final amount on the deposit if the money earns 6.4% compounded quarterly. So we just want to use the same equation as we used before. So let's label all of our variables. So we know that R is going to be 5,800. Our I is going to be 0.064. We're compounding quarterly, so 4 times a year. So we can't forget to divide by 4. And then our value of N is quarterly for 4 years. Since we know that we're depositing this money at the end of each quarter for 4 years, so this means 16 payments. All right, and then we just want to use the equation that we've already been working with. So we get that S is equal to 5,800 times 1 plus I, which in this case is 0.064 divided by 4 to the power of 16 minus 1, which is all going to be divided by 0.064, just divided by 4. All right, so as always, I invite you to work on this problem on your own. And if you do, you should end up getting, our final amount is $104,812.44. So if we're depositing $5,800 at the end of each quarter for 4 years, and our money earns 6.4%, which we're compounding quarterly, we know that our final amount is going to be $104,812.44. Now, Pete wants to accumulate $1,100,000 in the 4-year period. So what interest rate to the nearest tenth is going to be required? So in our last section, we talked about finding these values algebraically versus with graphing. And we can see that if you try to solve this algebraically, it's going to be just too hard to do. So we're just going to do Desmos in order to find this value. All right, so now we're on Desmos, and I have inputted our equation that we were working with. And then also we're going to set y equal to 1100,000 since we want to see when these graphs are going to cross, so we know what interest value we can find at $1100,000. All right, so clearly we can zoom out a little bit, zoom in, we see, well, our equation's definitely looking a little crazy here, but we have to go up to 1100,000, so we're going to zoom out quite a bit here, and we're just going to go keep zooming out. It's going to take a while, and here we go. So here's the line that we have here. And if we just scroll over, we just scroll over this point here, it's going to tell us 0, 1100,000. And then if we kind of move over a little bit, it's going to tell us 0.089. So this graph is really funky. It's got two different values. But something that we can do to make this a little bit more clear is we're going to use this graph settings tool on the side here. It's going to give us a bunch of different settings. And what we're going to do, since we know that our rate has to be between 0 and 1, or 0 and 100%, we're going to set our base value to 0 and our largest x value to 1. Now we clearly see when these values are going to cross, and we see it's going to be at 0.0889. So we see that's going to be about 8.9%. So let's head on back to our notes and write that in for us. All right, so we use Desmos in order to find that our interest rate, rounded to the nearest tenth, is going to be, I is going to be about 0.08889, or about 8.9%. So we're able to find that value using Desmos instead of trying to solve this algebraically, because we would have been in a very large mess if we had tried to do that. I'm going to move my image back up. All right, so now moving on to example 4, which is also number 13 in your book. We're going to find the amount of each payment to be made into a sinking fund to accumulate the given amount. Payments are made at the end of each period. So we know that this is an ordinary annuity since payments are being made at the end of each period. So we have $11,000 and our money is earning 5% interest, which is being compounded semi-annually for 6 years. So let's establish our variables. We know that R, or what we're trying to find is R, so we don't know R yet. But we have S is going to be $11,000, because this, we already know our future value. We want to find how much we need to pay for each payment. So S is 11,000. We have I is 5%. It's being compounded semi-annually, so twice a year. So we have 0.05 divided by 2. And then we have our N value, which it's happening, or it's being compounded semi-annually, so twice a year for 6 years. So we get that our N value is going to be equal to 12. Now we want to solve this using the same equation that we had before, but now we're solving for R instead of S. So on our equation here, we're going to say $11,000 is equal to R times 1 plus 0.05 divided by 2 raised to the 12th power minus 1, and this is all divided by 0.05 divided by 2. So what I'm going to do is I'm going to calculate everything in here. So everything within the brackets I'm going to calculate, and I invite you to calculate on your own. And if you had, you should have gotten 11,000 is equal to 13.785 times R. Now we want to divide by our value of 13.785. And this is going to give us our value of R, which I also invite you to calculate this on your own as well, which you should have gotten $797.39. So we know, calculate first, just so we know what order that's in. So we know that if we want $1,100,000 with a 5% interest rate compounded semi-annually after 6 years, we're going to have to make payments of $797.39 semi-annually for 6 years in order to get $11,000. All right, so those were our sinking funds. Now we're going to get into annuities due. So we've worked with our ordinary annuities, and now we can modify our results slightly to apply annuities due where payments are made at the beginning of each period. So now instead of at the end of each period, we're working with the beginning of each period. So we have the future value of annuity due. The future value S of an annuity due used to accumulate funds is given by, now we have S is equal to R times 1 plus our interest rate to the power of N plus 1, so now we have N plus 1, minus 1, all divided by our interest rate minus R. So this is telling us that S is equal to an ordinary annuity minus our one payment of N plus 1 payments. So we're basically, what we're doing is we're subtracting our very first payment from our ordinary annuity. We know that R is the payment at the beginning of each period, I is the interest rate per period, and N is the number of periods. So to find our future value of an annuity that is due, this is the equation that we're going to solve. So to put this into practice, we have example 5, which is also checkpoint 6. And we are going to say that Ms. Black deposits $800 at the beginning of each 6-month period for 5 years. We want to find the final amount if the account pays 6% compounded semi-annually. All right, so we want to use this equation that we just learned, and we're going to set up we're going to establish our variables. So we know in this case, R is going to be $800, or 800. Our interest is 6%, or 0.06 semi-annually, so twice a year, so we're going to divide by 2. And then our N value, if it's semi-annually for 5 years, that's going to be 2 times 5. So our N value is going to be equal to 10. So now we just want to plug all of these values into our equation over here. So we're going to get S is equal to R, which is 800, times 1 plus I, which is 0.06 divided by 2, to the power of 10 plus 1, since we know it's N plus 1, minus 1, all divided by 0.06 divided by 2, minus $800. All right, so let's just simplify our equation just a little bit. So we get 800 times 1.03 to the 11th power minus 1 divided by 0.03 minus $800. So I invite you to calculate this entire value on your own. And if you should have gotten S is equal to $9,446.24. So this is what we've gotten for our final value. Now we want to find our final amount if the account were an ordinary annuity. So now we're calculating our value of the account if we were paying at the end of the period, because all this is really saying is that in one case we're working with our payments at the beginning of each period. So our annuities due is working with we're applying our annuities when payments are due at the beginning of each period, and our ordinary annuities is when payments are due at the end of each period. So it's really the only difference between these equations, concept-wise, not equation-wise. We know that they are different equation-wise. So if we're finding the final amount of this account, if it were an ordinary annuity, meaning if we were paying at the end of each period, all we have to do is use the equation that we have been using. So as a reminder, it's S is equal to R times 1 plus I to the n power minus 1 divided by I. So this is the equation that we're going to use if we're working with an ordinary annuity. So since we know all the same values, we're going to get S is equal to 800 times 1 plus 0.06 divided by 2 to the 10th power, because now we're not working with n plus 1, we're just working with n, minus 1 divided by 0.06 divided by 2. And since we already know the values, if we simplify it a little bit, let's just simplify it a bit here so we can get S is equal to 800 times 1.03 to the 10th power minus 1 divided by 0.03. I invite you to calculate this value on your own. And if you do, you should end up with $9,171.10. So we see our final amount in the case of when we have annuities due, or if we're paying at the beginning of each period, we're going to end up with a larger final amount than if we were paying at the end of each period. So those are just those slight differences there. And all right, that finishes up our section 5.3. So we see that this section was a little bit challenging than the last. So please, please, please do not hesitate. If you have any questions, email me, drop by my office hours, submit an anonymous question if you would like into our anonymous homework form. So yeah, I will see you virtually later. Goodbye.